The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are two different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmail@ybcc.edu and I'll respond as soon as I can. All right, so this morning, eventually, we're going to take a look at section 11.6 and 11.7. And it may seem like a lot, but we're not going to do a whole lot in 11.6, but we'll get to that in a little bit. Right now, we're going to find a blank page. There we go. We're going to take a look at, this is a problem from section 11.5, part 2, number 5. And you should see it there on the web assigned screen on the left side. It says, Kuwait, located at the head of the Persian Gulf, has one of the greatest population growth rates in the world. Bulgaria in southeastern Europe has one of the smallest. Use an exponential growth decay model to complete the table. So basically, we're talking about this formula, A equals PE to the RT power, okay? So for Kuwait, the starting population in 2010 was 2,789,132. The annual growth rate, R, is 3.501%. So to change that into a regular number, we move the decimal 2 places to the left. Let's see, 1, 2, okay. We want the estimated population in 2020, which is 10 years later. So T is 10. So there's our numbers. We'll plug them in. A equals 2,789,132 times E to the 0.03501 times 10 power. So A equals, let's see here. Put on the little glasses so I can see. 2,789,132 times E to the 0.03501 times 10. Close it up. And we get 3,958,36. 2.526. It says to round to the nearest integer, which would be right there. So the next place over to the right would round up. So 3,958,363. So the new population would be 3,958,363. Any questions about that particular example? All right, let's take a look at the second one, which is Bulgaria. We're going to use the same formula. Now, the initial population in 2010 is 7,148,785. The annual growth rate is negative, which means the population is decreasing, negative 0.768%, which would be negative 0.00768. Let's see, is that right? 1, 2 places. Again, the time is 10 years. So A equals 7,148,785 times E to the negative 0.00768 times 10 power. So once again, going to the calculator, 7,148,785 times E to the negative 0.00768 times 10. Close it up, and we get 6620311.427. The 4 would round down, so 6620311. So 6,620,311. Any questions about this example before we go on? All right. So I'm going to switch to the other screen. Let's see here. Maybe. All right. Give me just a minute here to switch things up. Okay. So now you should be seeing just the whiteboard screen. Can I get verification of that from somebody?
Yep.
Thank you. Okay. Back in the beginning of this chapter, I introduced the following problem. I said 2, now let's try that again. 2 to the 3rd power equals 8. 2 to the 4th power equals 16. And I said 2 to what power equals, I think I chose 11. Okay. So we determined that x had to be larger than 3 and smaller than 4, but we'd have to use a trial and error process to get there unless we used logarithms. So what we're going to do is we're going to take 2 to the x power equals 11, change that into a logarithmic equation, which would be log base 2 of 11 equals x. And I think we got that far with it. But the problem now is we don't know how to deal with log base 2 of 11. Our calculators will deal with log base 10, or just log, or log base e, or ln, natural log. However, there is a formula called the change of base formula that allows us to take a problem like this, where the base is something other than e or 10, and convert it into a problem where the base is e or 10. So first of all, I'm going to rewrite this equation and put the log on the right-hand side, okay? The formula for the change of base, and let's write this here, change of base formula. Can't spell worth a darn. That doesn't work. Let's see here. Come on. Formula looks like this. If you have log base b of x, that equals log base a of x over log base a of b. Now, a can be any acceptable base. Recall the restrictions on a. It has to be what? Greater than 0 and not equal to 1. But we would deliberately choose either base 10 or base e. So this means that log base 2 of 11 could be written as log base 10 of 11 over log base 10 of 2. That is to say, we could write log of 11 over log of 2 with the implied base being the 10, okay? Or we could write log base e of 11 over log base e of 2. That is to say, the natural log of 11 over the natural log of 2. But we have to have the same base on the top as the bottom, as on the bottom, okay? All right. So let's go to the calculator and see what we get. If I use log base 10, log base 10 of 11, close that up, divided by log of 2, close that up, I get 3.459. We'll just go out to the 1,000th place for now. And then if I use natural log of 11 divided by natural log of 2, I get the same number, 3.459, etc. Okay, so that means that 2 raised to approximately the 3.459 power is 11. Now I say approximately because I rounded these numbers off, okay? If I, and I could have carried it out 10 decimal places, but anyway, so this formula will allow you to take a problem with a base other than a 10 or an e and convert it into a problem with a base of 10 or e. Now, it doesn't matter whether you convert it to base 10 or to base e, but make sure you don't have like the top one base 10 and the bottom one base e or something. They have to be the same base in that change, okay? And in some situations, it's more advantageous to use base 10, in others, base e. We'll see that as we go along. Anyway, any questions so far on this? All right, I want to just run through some more examples. Why doesn't that want to stay on the draw feature? I don't know. Okay, why am I talking to myself? I don't know that either. Let's say I've got log, whoops, log base 7 of 3. It says use the change of base formula to find each logarithm to 4 decimal places. So this would be log of 3 over log of 7, or I could have used natural log of 3 over natural log of 7. Log of 3 divided by log of 7. And I get 0.56457, et cetera, et cetera. It said to the 4 decimal places, so right there. The 5th place, the 7 would round up, so 0.5646. And again, if I use natural log of 3 over natural log of 7, I should get the exact same thing. All right, let's see. Here's another example. Log base 1/2 of 6. So that would be, let's use natural log this time. Natural log of 6 over natural log of 1/2. And that is natural log of 6, close it up, divided by natural log of 1/2. Okay. And that is negative 2.58496. Here's the 4th place, the 6 would round up, so negative 2.5850. Okay. And let's see, one more case. Log base pi of e. So that would be the natural log of e over the natural log of pi. Okay. Well, let's see here. Natural log of e. Okay. Divided by the natural log of pi. And I get 0.87356. So the 5 would round up because, well, the 6 would round up. So we get that. Any questions about that? Okay, so that's the only thing we're going to take from section 11.6 is this change of base formula. So you'll have a short assignment, a few problems to work on that. And now we're going to go on to section 11.7. And let's see here. So this is 11.7. Now, we've already looked at this equation, A equals P times e to the RT power. We've also had what? A equals P times 1 plus R over K to the KT power. And we've had T equals the natural log of 2 over R. I think that about covers it so far in this chapter. Okay, so we've got what the compound interest formula for when it's not compounded continuously, the formula used for continuous growth or decay, which can be used in populations. And then if we're looking how long it takes to double something that's growing continuously, we take the natural log of 2 divided by the growth rate, and we get the time. All right, in this next section, there are 2 new formulas. One of them is this. And if you look at it closely, it's really the same formula as we've had before. P with a little 0 is called P naught, or think of it as an O, P original, sort of the original amount, and then over here is the final amount. But if you look at it, the T's are the same, K and the R represent the growth rate, E is still E, beginning amount, ending amount, beginning amount, ending amount. So we've got that formula. It doesn't matter whether we use this form or this form, it accomplishes the same thing. Okay, and then there's another formula that's called the radioactive decay formula. And I want to look at that one. Looks like this. So A equals A sub 0 times 2 to the negative T over H power. Okay, now this is a half-life formula, and let me explain that, and then we'll go back and look at the formula some more. if there's a radioactive substance, there's a certain amount of radioactive molecules or whatever in there. I'm not a chemistry major, but over a certain period of time, half of that goes away. And whatever that time is called the half-life. But let me just take an example. Let's say I've got 64 Snickers bars and I put them in a refrigerator. And I come back 1 week later and I discover that there's only 32 of them. So in 1 week's time, half of them disappeared, or we'll say died off, okay? I come back 1 week later and there's 16 of them. I come back 1 week later and there's 8 of them, and then 4, and then 2, and then 1, and then a half, and then a quarter. So as each week goes by, at the end of that week, we have half the amount we had at the beginning of that week, okay? So the first week you lose half of 64, which is 32. The second week you lose half of 32, which is 16. It's not a case of where the first week you lose 32, the second week you lose 32, and there's nothing left. Each week, half of what was there at the beginning of the week disappears. So for this problem, the half-life would be 1 week, okay? Any questions about that? All right, now, I want to talk about this formula. If we had 2 to the t power, let's say we had y equals 2 to the t power, okay? And we graphed that thing. Every time t increased by 1, the y value would double, okay? I graphed y equals 2 to the x several days ago, okay? But what if I had y equals 2 to the negative t power? I could rewrite that as y equals 1/2 to the t power. In other words, changing the exponent from a negative exponent to a positive exponent, we take the reciprocal of the base, okay? Why am I going through all that trouble? Well, if we take a look at this thing right there, that's the same thing as 1/2 to the t divided by h power, okay? Now, if I was writing this material on my own, I probably would have used this as the formula, just because it more quickly identifies, oh, we're talking a half-life there. But suffice it to say, this accomplishes the same thing, okay? So by having a negative exponent on the 2, it's like having a positive exponent on a half. T is the time that happens, and h is the half-life of a given substance. A sub 0 is the beginning amount, and A is the ending amount. Let's see if we can put that to work. Okay, so we've got this formula, A equals A sub 0 times 2 to the negative t over h power. The problem says, tritium, I'm not sure if that's how you pronounce it, but tritium decay. The half-life of tritium is 12.4 years. So the half-life is 12.4 years. How long will it take? So that's time. For 25% of a sample of tritium to decompose. All right, they did not tell us the beginning amount. And they didn't tell us the ending amount. But they did tell us this. It says, how long will it take for 25% to decompose? So if 25% of the beginning amount goes away, the ending amount is equal to 75% of the beginning amount. Did you follow that? You okay with that? Anybody still alive? Okay, well, hopefully you did.
Yes.
Okay, just making sure. I know no one likes to talk. So I'm going to have 0.75 a sub 0 equals a sub 0 times 2 to the negative t over 12.4 years. Okay, since the half-life is in units of years, the time will be in units of years as well. Okay, now Again, recall, they didn't tell us how much was there at the beginning. They only told us that we lost 25% of it. But that's okay, because the next step I'm going to do is to divide both sides by that, whatever that beginning amount was. So now I've got 0.75 equals 2 to the negative t over 12.4 power. I now have an exponential equation in the form that I can use to convert it to a logarithmic equation. Okay, so I would get log base 2 of 0.75 equals negative t over 12.4. So we okay with that? Base is the same, players change. All right, I'm trying to solve for t. So now I'm going to come back and I'm going to multiply both sides by negative 12.4. The 12.4 gets rid of the 12.4 in the denominator, and negative times negative makes it a positive. So now on the right side I have t, and on the left side I have negative 12.4 log base 2 of 0.75. Okay, so I've isolated t. I've solved for t. Only now I'm going to punch that into the calculator to get a decimal approximation. Okay, to do that, I'm going to use the change of base formula on this piece of the problem. So t equals negative 12.4 times the log, and I'm going to use log base 10 of 0.75 divided by the log base 10 of 2. Okay, so I'm going to punch that into the calculator. And let's see what I've got here. Negative 12.4, and then times the log of 0.75, close that up, divided by the log of 2, close that up, and I get 5.14646, etc. Now, since years were given to the nearest tenth, we'll round our answer to the nearest tenth. The 4 would round down, so the time would be 5.1 years, approximately. Okay. Any questions about this problem? Anything you want me to go over again? I know there's a lot going on there. All right, we're going to do another problem. It says radioactive decay. In 2 years, 20% of a radioactive element decays. Find its half-life. So A equals A sub 0 times 2 to the negative t over h power. Time is 2 years. We're to find the half-life, so that's the unknown. Okay, it says 20% of the radioactive element decays. So we're starting out with this much, and we're ending up with that much. We're losing 20% of the original amount, so we have 80% of the original amount at the end, 80%, 0.80 or 0.8. Okay, so 0.8 a sub 0 equals a sub 0 times 2 to the negative 2 over h power. Again, I'm going to divide both sides by a sub 0, or a naught, as it is sometimes referred to, and I get 0.8 equals 2 to the negative 2 over h power. Now I can convert this into a logarithmic equation. Log base 2 of 0.8 equals negative 2 over h. Now, things are a little trickier here. I'm trying to solve for h. I can't just get rid of the negative 2 because the h is in the bottom, so that would be like 1 over h. So I've got to get h up on top. So I'm going to multiply both sides by h. That's going to give me h. Log base 2 of 0.8 equals negative 2. Okay, so those would cross out. But again, I'm trying to isolate h. So now I'm going to divide both sides by log base 2 of 0.8. Log base 2 of 0.8. So now what I've got is this. I've got h equals negative 2 over log base 2 of 0.8. But I need to use the change of base formula. So let's see. I'm going to recopy this on the next page. H equals negative 2 over the log base 2 of 0.8. Okay, so that would be negative 2 over log of 0.8 over log of 2. And what I'm going to do, I'm going to put parentheses around this whole thing so that I'm taking the numerator divided by that whole denominator. So in my calculator, negative 2 divided by parentheses log of 0.08 divided by log of 2. And this is going to have parentheses, and that's going to have parentheses, and that's going to have parentheses. So let's see what we get. Negative 2 divided by parentheses log of 0.8, close that up, divided by log of 2, close that up, close up the whole thing. And I get 6.2125, etc. Again, they rounded to the nearest tenth, so 6.2, and this was years. Do you have any questions about how I put all that into the calculator? We're okay with that? Okay, okay. Next example. Carbon-14 dating. A bone fragment analyzed by archaeologists contains 60% of the carbon-14 that is assumed to have had initially. How old is it? Okay. So because we're dealing with carbon-14, which is a radioactive material, this is a half-life situation. So A equals A sub 0 times 2 to the negative T over H power. A bone fragment analyzed by archaeologists contains 60% of the carbon-14 that is assumed to have had initially. How old is it? Okay, so we need the half-life, we need the time, and we need the beginning amount. All right, now, it doesn't tell in these directions, but on an example previously, it says that the half-life of carbon-14 is 5,700 years. That is not something I would expect you to have had memorized, okay? How old is it? So the time is the unknown. We don't know the initial amount. Now be careful. The previous two problems, the first one said 20% decays. So we had, oh wait, the first one said 25% decays. So we had 75% left. The second one said 20% decays. So we had 80% left. This one says it still contains 60%. So it doesn't tell you how much went away. It tells you how much is still left. Okay. And my intent is not to trick you, but you need to read these problems carefully. Are they telling you what's gone away or what's still left? Okay, so it still has 60%. So now we've got 0.6 A sub 0 equals A sub 0 times 2 to the negative T over 5,700 years power. We're going to divide both sides by A sub 0. So 0.6 equals 2 to the negative T over 5,700 years power. Like one of the ones we did earlier, we're going to multiply both sides by negative 5,700, because then the 5,700s reduce out, the negatives become a positive, and we've got, let's see here, negative 5,700 times 0.6. What's that? Oh, you know what? I messed up. Yep, I messed up. Big time, big time. I thought something's wrong here. I made a rookie mistake. I can't do that yet because this is an exponent. My writing's so sloppy, it's hard to tell. Negative t over 5,700. I can't go in there and deal with an exponent because it's attached to a base. What do I have to do first? Anybody? No volunteers? I've got to change it to a logarithmic equation. So this becomes log base 2 of 0.6 equals negative t over 5,700. So this was an exponent. I can't go in there and just multiply by part of an exponent. But here it's just a regular number. Now I can go in and do what I was trying to do before. So now I'm going to multiply both sides by negative 5,700. I made that rookie mistake so that you wouldn't have to, okay? So the 5,700s reduce out, the negatives reduce out, and I've got what? T equals negative 5,700 log base 2 of 0.6. So T equals negative 5,700, change of base, log of 0.6 divided by log of 2, calculator time. And negative 5,700 log of 0.6 divided by log of 2, and I get 4200.7. So we're going to say about 4,200 years. All right. Any questions about that? Okay, let's go back to a problem that we dealt with earlier. It says compound interest. If $500 is deposited in an account paying 8.5% annual interest, compounded semi-annually, how long will it take for the account to increase to $800? So my question to you is this. Which of those formulas am I going to use? Let me read it to you once again. If $500 is deposited in an account paying 8.5% annual interest, compounded semi-annually, how long will it take for the account to increase to $800? Which one? The first one or the second one?
The second one.
Why?
Because it's not continuous. It's
correct.
Certain amount of time.
Good job. Okay, let's see. What does it say? $500 is deposited in an account paying 8.5%. Don't mess up converting the percent into a decimal. That's the place people make the most mistakes. Compounded semi-annually, so that's twice. How long will it take for the account to reach $800? So now T is the unknown. So we've got $800 equals $500 times 1 plus 0.085 over 2, all raised to the 2t power. Okay. Now, I can take 0.085 divided by 2 and come up with a nice number. If I can't, if it ends up being some long decimal mess, then I'd have to keep it there, okay? But I'd have to keep it in that fraction form, or that 1 plus that fraction. But let's see what we get. If I take 0.085 divided by 2, this problem becomes this 1 plus 0.0425 to the 2t power, okay? Well, since that came out nicely, I can take what's in the parentheses and write it as 1.0425 to the 2t power. I should have left more room there. Let me write that down below. So $800 equals $500 times 1.0425 to the 2t power. Okay. I need to get it in the form where I can convert it to a logarithmic equation. So I got to get rid of that. So I'm going to divide both sides by $500. On the left side, I get what? 8/5. On the right side, 1.0425 to the 2t power. So I have a number equals a base to an exponent. I can now convert that into a logarithmic equation. Okay, we're going to have log base 1.0425 of 8/5 equals 2t. Okay, next I'm going to divide both sides by 2 to get t by itself. But instead of doing that, to make things a little easier to put into the calculator later, isn't dividing by 2 the same thing as multiplying by a half? So in other words, instead of doing that on both sides, I could do that on both sides. Further, isn't a half 0.5? You know what, let's just go with a half. So I'm going to multiply both sides by 1/2. Okay, so on the right side, the 2 and a half reduce out, and I've got t. On the left side, I've got 1/2 log base 1.0425 of 8/5. I'm going to recopy that, or copy that on the next page. I'm going to put time on the left side. So t equals 1/2 the log base 1.0425 of 8/5. Okay, which is 1/2 times the log of 8/5 divided by the log of 1.0425. And again, I could change a half into 0.5. I could change 8/5 into 1 3/5 or 1.6. However you want to do that. All right, so what do I got? I've got parentheses, 1 divided by 2, close parentheses, so a half times the log of 8 divided by 5, close it up, divided by the log of 1.0425, close that up, and I get 5.646140295. But what are we doing here? It said, how long will it take? And they rounded to the nearest 10th, so the 4 would round down, so about 5.6. 5.6 years. Okay, now let's go back and do the same problem, only now let's do it where it's compounded continuously. So instead of using this formula, we're going to use the other formula, because it says, yeah, just how long will it take if the interest is compounded continuously? So A equals PE to the RT power. $500 was the starting amount. The annual interest rate was 8.5%. And the final amount was $800. And it says what? How long will it take? But it's compounded continuously. Okay, so we've got this $800 equals $500 times e to the 0.085 t power. I'm going to divide both sides by $500. Okay, so this reduces down to 8/5 equals e to the 0.085 t power. 8. We're going to change it into a logarithmic equation. Log base e of 8/5 equals 0.0585t. Oh, but log base e, that's natural log. So natural log of 8/5 equals 0.085t. Divide both sides by 0.085. We're not going to have to use the change of base formula because since one of them was base e, we could just deal with it. So that divided by that. And let's see here. Natural log of 8 divided by 5, close it up, the whole thing divided by 0.085, and we get 5.529, so 5.5 years. Now that's rounded to the nearest tenth, but before we got 5.6 years, right? So having it compounded continuously, it grows faster. Okay. All right. So this is the last new material. Over the weekend for Monday, you need to do 11.6, some problems to do with the change of base formula. You need to do 11.7 and the chapter review material. Okay. On Monday, we're going to review for the chapter 11 test. Tuesday, you'll take the chapter 11 test. When we come back after Thanksgiving break, we'll spend that week reviewing each of the different chapters for the final exam that comes up. What is it? Anyway, it's on a Monday. Okay. So any questions about any of that before we go? All righty. I'll be back at 1:15. Should you have any questions, have a great weekend.